Hey, hello guys. Today we are going to see the moment of inertia of a 1D uniform rod. Right? So let's get started. So this is our one-dimensional rod. It's considered as one-dimensional, and the thickness of the rod is very small. And we are considering the thickness of the rod is very small. Okay, so this is basically one-dimensional uniform rod, and we are going to calculate the moment of inertia. Right? So basically we have learned in center of mass we used to calculate the center of mass of different objects, right? We take a small dm mass. Actually this is a continuous mass. Sorry for the wrong spelling, but for continuous mass system, so the mass is uniformly spread throughout, right? So we usually take a small dm mass, right? We usually take a small dm mass. Okay, so we take a small dm mass of width x. Okay, let's call it as dx, and then mass dm. So this as mass dm and length dx. So we are going to calculate the moment of inertia of this along this axis of rotation. So let's consider this as an axis of rotation, and let's take it as 0, and the distance from the axis of rotation to the right hand side end is L by 2, or take it as let's take it as L by 2, and then this side will be minus L by 2, right? So we are going to calculate the moment of inertia by using these information. Okay, so what is the formula to calculate the moment of inertia of a continuous mass particle? For discrete particles we use I equals to m1 r1 square plus m2 r2 square till up to mn rn square, right? So for discrete particles we use integration. We just calculate the moment of inertia of the small part and then integrate it to sum up all the small dm masses, right? We use integration by putting their limits. All right, so let's integrate. So basically what should we do to integrate? So di, which is I integration, is equals to integration of, what is the formula of moment of inertia? Moment of inertia is nothing but mr square, right? Mr square. So here it will be m integration of mr square, which is dmr square, the small mass, right? The small mass is dmr square. So let's calculate the moment of inertia of it. So okay, right, let's take the distance of this small dm mass from the axis of rotation is r. Okay, so r square. Okay, this distance from the axis of rotation to the dm mass, which is r square. Okay, so here we have to integrate it. So let's put out the values. Integration of here if we can take only this mass and then integrate everything by putting the limits. So what will be the limits? The limits will be minus L by 2 lower limit to L by 2 to upper limit, right? So basically we'll get all these things. So minus L by 2 to plus L by 2. Okay, so this will be our limits. So let's integrate it. Integration of di, which is I, is nothing but integration of minus L by 2 to plus L by 2, integration of dm r square. Okay, so it will be, if we integrate this, how do we integrate this? First of all, see the variable, it's dm dr. We usually integrate like this, right? X square dx. y square dy. So there's different variable here. How to integrate it? There's nothing. It's very simple. See, in center of mass, we have learned a different thing: mass per unit area, mass per unit length, mass per unit area, and many other terms for 1D, 2D, and to calculate the surface area. So we have only one dimensional rod, which is 1D. So we are gonna use a variable called lambda, which is mass per unit length. Okay, so mass per unit length. So lambda is nothing but for 1 meter. So we know mass by length is nothing but lambda, right? Yes. So for 1 meter length, it will be lambda. 2 meter, it will be 2 lambda. For dx, it will be lambda dx. For dr is lambda dr, right? So thus by this we know that the dm mass can be written as lambda dr. Okay, this, so by this we can substitute in our integration and then we can get the values. Let's do it. Actually, I don't have a proper phone holder, or else the video quality and the alignment would be very good, but I'll try next time. So the moment of inertia will be integration of d lambda, which is constant, r square dr. Okay, so we have to integrate it. So lambda will come out of the integration and we have to add limits, right? So minus L by 2 to plus L by 2 r square dr. Oh, I don't have enough space in board. I'll just erase it. I'm sorry guys. So I'll do it here. Di is equals to r, which is I, is equals to minus L by 2 to plus L by 2, lambda is outside, r square dr. Okay guys, so let's integrate it. I guess you know integration very much, pretty good. So r square, if we integrate, it will become r cube by 3, and putting the limits on L by 2 to minus L by 2, it is nothing but lambda. So substitute the limits, it will be L cube by 8, right? L cube by 8 by 3 minus L cube by 8 by 3, and then this will be the upper limit minus lower limit. The lower limit is L minus L cube by 8 by 3. Okay, so if we add both, we get lambda. The 3 will go to the denominator. This will become L cube by 24 minus of minus is plus, L cube by 24. So 2L cube by 24 will be our answer. 2L cube by 24. We cancel this to get 12, and then lambda L square by L cube by 12. So we know the lambda value is nothing but m by L, right? So let's substitute it. M goes up and L gets cancelled, so the final answer will be ml square by 12. Hope you liked it. Keep watching guys. Thank you. Bye.